So in this example, we will calculate the magnetic field using Ampere's law around a wire of non-uniform current density and a solid interior. So we'll also calculate the magnetic field inside as well. So actually, let me draw this a little thicker. Okay, along this wire has a current that runs to the right. This wire is of radius r, and it's a solid, right? A solid wire. So, part A, let's find it, say, outside. Oops. Outside the wire. Or in other words, when r is greater than capital R, right? Using Ampere's law, we need to draw an Amperian loop. So I've done that as such, right? And that Amperian loop is of radius r, right? So we can write down Ampere's law. The closed integral of b dot ds is equal to the constant mu naught times the current enclosed within that Amperian loop, right? And this is essential. Ampere's law must have two things. Well, it must have several things, but the two most important is that this integral be a closed loop, right? And so we'll see that that deals with this Amperian loop has to be a closed loop, right? It can't have a loop with some space in between. It can't be a hoop or a horseshoe pattern. It has to be closed. The second thing is that this current must be the current inside that Amperian loop, right? Or enclosed within that loop. In that case, or in this case, it's the current I, right there. Okay, so this Amperian loop I've drawn is at a distance lowercase r from the central wire axis. And as we move around, let's say we have a vector ds, right? And like normal, we have several ds's around here. And they're all tangent to this Amperian loop. And they're all at 90 degrees to this vector here, right? They're all at right angles. So when evaluating the left side of Ampere's law, that's a dot product, right? It's not simply multiplication. So we have closed integral of the magnitude of that dot product, which is the magnitude of both vectors. Sorry, so that's just b, and the magnitude of ds times the cosine of the angle in between. And the right side, since we are doing this for an Amperian loop outside the maximum radius, the current enclosed is simply the current in the wire I. Okay. On the left side again, the magnetic field, because this is a steady current, right? The value of I is unchanging. That means that the magnitude of the magnetic field is also unchanging. Okay, it's also not changing direction. Speaking of direction, if you put your thumb, your right hand thumb, in the direction of I, your fingers should naturally curl this direction, right? Such that in front of this wire, they're moving down, or rather, the field would move down. Behind the wire, it would move up. And on top, it would move towards you. The bottom would move away. Okay, so we call that direction. Let's do it here. That is the phi direction, the phi hat. In cylindrical coordinates, it's the phi hat direction. But for the left-hand side of this equation, that magnitude of b is constant, so we can pull that out of the integral. In addition, what's the angle in between b and ds, right? If that's the case, let's do this in blue. The magnetic field is going around the loop. It's going down, down. It's actually going in the same direction as the ds is at every point along this Amperian loop, right? And so because of that, the angle is 0, and thus cosine of 0 is 1. And because of that, that goes away. So the left side just becomes b times the closed integral of ds. The right side stays the same, mu naught times I, right? And so solving for the magnitude of the magnetic field, well, sorry, I'm getting ahead of myself just a little bit. That closed integral, well, what's S? That's the total path length. That's the circumference of that Amperian loop. So b times 2 pi times lowercase r, 2 pi r. So the magnitude of the magnetic field is simply mu naught I over 2 pi r. And the direction is in the phi hat direction, right? And this means that when you are on top of this Amperian loop, the field is coming out of the screen. When you're on the right side, it's going down. When you're on the bottom, it's going into the screen. When you're on the back, right, or left side in this case, it's going up, okay? So that direction. So that's part A. Part B, let's deal with inside this loop, okay? Let's take a look inside. So inside, we'll say wire, or in other words, when R is less than capital R, all right? We have to draw another Amperian loop in that case. So let me do that. Let me just choose some random radius, right? This is at a distance now of, well, we'll call it lowercase r again, okay? And I may need to redraw it a little bit larger, but can you see how the amount of current flowing through this smaller Amperian surface will be some percentage of the total current flowing through the entire wire, right? The current in just this little bit will be some percentage of the overall current. So we need to calculate that, right? That's one of the things that we need to calculate, again, using Ampere's law, okay? So I'm going to do that on the other page right here. So we have closed integral of b dot ds is equal to mu naught times the current enclosed, right? That's Ampere's law, and that's in purple. I just realized that. Oh well. This is unchanging. We need to figure out several things. We need to figure out the angle in between b and ds in this part B, and we need to find out what I enclosed actually is, right? Or at least we need to find a general expression. Because what if we have this Amperian loop, say, at a slightly larger r, right? Or what if it's at a slightly smaller r? Well, we need to have some general expression for the current enclosed such that we can use that in all cases, okay? So, to start, I predict that I enclosed will be some number, right? Whoops. I enclosed should be some number, some ratio, some percentage of the total current I. Okay? That's what I'm predicting. So let's try and find that. Okay? So I enclosed, oh crap. What I haven't told you is that this is a solid wire and it's a non-uniform current density. I haven't even told you that non-uniform current density relationship. I need to do that. So this is, well, this is rho, right? The volume charge density. Well, let's use J for the current density. Okay, so in part B, the current density is equal to KR. Okay, this is the current density in every section, in every length of this wire, right? So in other words, the current density varies radially, not linearly, if that makes sense. Right? So, the current enclosed, we need to find out what that is. That is actually the integral of J, right, our current, which is a function of radius, times dA. Where do I get this from? Well, the definition of the current density itself. J is defined as the current per area. And so that's how I get the value for I, is J times A. In this case, though, what's the area? Well, it's the area of every cross section of this wire, right? So really, that's the area of that disk or that circle. So that's the current divided by the area of every circle, pi r squared. Now we need to get dA, though. So, oops. Right, so if area is pi r squared, dA is the derivative of that with respect to radius. And this is what I plug in right there. Okay. I also plug in the value for, the expression for the current density, K times R. And K is just a constant. We'll actually find out what it is shortly. And then plug it in dA. That's 2 pi r dr. Okay. By the way, this value or this expression Kr, I just came up with that, right? That's an example current density. That's an example of a non-uniform current density. I just made that up, okay? But we're going to use it and incorporate that radial dependence, okay? And in fact, right now is when we need to see what K is, right? What this constant is. So, let's see. It's a constant, so it comes out of the integral, as does the 2 pi. And so we have then the integral of r squared dr. Okay. Now, we need to know what K is, so how do we find out the value for that constant? Well, the value for the current overall, I, that's a constant. Okay. And so let's utilize that to solve for an expression for K. And to do that, we need to do this exact same process we did for I enclosed, but for the current, right? This is the total current in the entire wire. So we have the current density J times dA once again. So we have K and R just like above, and dA just like above as well. Okay. However, now we're integrating from 0 to the maximum radius of the wire, which is capital R. Okay. And so we will get an expression that's entirely a constant value. 2 pi K comes out, and we integrate from 0 to R of R squared dr. And this gives us, what is that? Capital R cubed over 3. And that's the value for the entire current through the entire wire. And the 2 pi is constant. The capital R is constant. So thus we can solve for an expression for our K value. Right? And this expression here is constant. That's what I plug in way up here for the I enclosed current. Right? Two different currents. The I enclosed is the current through our Amperian loop. This current down here is the total current through the entire wire. Okay? So now, let's go back to our I enclosed calculation. And with that plugged in, we see that a 2 pi cancels. We have a 3 I, we have a capital R cubed on the bottom, and now we integrate our r squared dr. And as far as I enclosed goes, we're integrating from 0, well, to lowercase r, to the radius of our Amperian loop. And again, don't tell your math teachers there should be, primes by these or whatever to differentiate the r's, but I trust that you can follow along. So 3i over capital R cubed, integrating that gives us lowercase r cubed divided by 3. The 3's go away, and, well, let's do this. Let's write it with the ratio first. We have a ratio of r cubed divided by capital R cubed times our entire current. Just like I said, what happened up there. We have some ratio, right? Some percentage. The radius for our Amperian loop cubed divided by the entire radius of the wire, right? And so the enclosed current will be some percentage that's less than 1 of our total current. And now we can plug this into Ampere's law above, okay? So keep this expression in mind. Let's do it over here. We have closed integral of b dot ds equals mu naught I enclosed. All right, so in our Amperian loop, if the current stays the same or constant, the magnetic field value stays constant and can be pulled out. For enclosed, we plug in what we just found. All right. This closed integral of ds, just like in part A, is 2 pi, but now it's times the radius of our Amperian loop, lowercase r. The right side stays the same, mu naught I over that. And one term of lowercase r goes away, and thus we have for our magnetic field, mu naught I over 2 pi r squared over r cubed. And the units are the same as in part A, mu naught I divided by one factor of radius, right? One factor of a distance. So the units are correct. And the direction is the same as in part A, the phi hat, right? And so this would be our answer when r is less than capital R, and if, let's see, if the radius is the same as capital R, right? If we're actually on the surface, well, that reduces down to that, right? Our normal mu naught I over 2 pi r. So if r equals that, right? So this was solving for the magnetic field in 3 different cases. When you have the Amperian loop outside a wire, when you have it exactly on the surface of the wire, and when you have it inside a wire with a non-uniform current density. There you go. Thanks for watching.